at another class of problem that we call 2D problems. Okay, so in this lecture, I will try to show you how to deal with the problem, the big class of problem that we can simplify a lot of things. Okay, so the one that I mentioned before apply for the general case for general three-dimensional bodies. But there are several cases that the data of the problem may be simple. Okay, some of the loading condition may be very simple, and the geometry of the body can be very simple, and you can just try. You can just reduce several things from the one that we have for the general case and make things simpler. That's what I try to say. So here, you will see the two commonly used condition for for simplifying the problem from 3D to 2D. Okay, and also I will try to show you a simple solution technique that people use to deal with the 2D problems. Okay, I will not show you how to directly solve the governing equation even for the 2D case. I will try to look at the simple strategy based on guessing the form of the solution again. But now it's simpler in the context that several equations can be reduced or can be removed. Some of the conditions may be satisfied automatically because of the simple information of the problem. Okay, and the solution techniques, the extensive solution techniques, I will move to the second class that I offer next semester. If you guys are interested in solving a big class of problems using using some special techniques, for example, crack problem, contact problems, those kind of things. So I will show you in the second class. But here I just show you the simple strategy similar to the previous lecture. Okay. So let's look at the problem description here. Okay. So I try to look at the cylindrical body again in this case. Okay. So you know the definition of the cylindrical body, right? This is definition. It's similar to the body that I mentioned before. Okay. In Saint Vernon case. So the cylindrical body that I focus on in that particular class of problem, we assume that okay, the length of the body is sufficiently large compared with the cross-section dimension, right? So in that sense, if the length of the cylinder is sufficiently large compared with the characteristic dimension of the cross-section, so that implies the existence of the interior zone, right? So once the interior zone exists, now you don't need to worry much about the distribution of the traction or the detailed distribution of the traction at both ends if you are interested in the interior zone. So that come up with principle of Saint Vernon that we looked at before. But here I will look at this different setting. Okay, I look at the same cylindrical body, but we will have some kind of different setting. You will see in a moment. So I use the length. The length, I define the length of the body equal to 2h. You can think about the length here, or you can think about the thickness. Okay, I look at the cylindrical body with the length 2h or the thickness equal to 2h. Okay, so if the body here is very thin, so if 2h here is very small compared with the cross section of the body, you may think about this as thickness, not the length. Okay. I define the axis. Okay, I will define the coordinate system in a moment. So here you are clear, right, about the definition of the cylinder. So the body is cylindrical if there exists a direction on the called the axis. That if you look at the cross section, okay, normal to that axis, okay, all the cross section normal to that axis are identical. Or I can say that the shape of the cross section is independent of the coordinate along the axis there, right? If you move along that axis, you see exactly the same cross section. Is that clear to you? Okay, so that is the definition of the body that we will focus on for this particular class of problems. Okay, how about the battery? Again, the battery of the body consists of 3 parts, right? The side face, okay, I use the same symbol as the previous problem, right? I use S pi here to represent the side face. And the top and bottom surfaces, I will use the symbol S1 and S2. So S1 here represent the bottom surface and S2 represent the top surface. Okay, so we have 3 portions of the battery here. Okay. So if you look in this way, if the body that we focus on is simply the cylinder, we can say that the geometry of the body is completely described by what? The cross-section, right? So whenever you know the cross-section and you know the thickness or you know the length, okay? So the thickness of the body and the cross-section are sufficient to generate the whole body here, right? Is that right? Because you can think about that you make a copy of the cross-section in the coordinate direction and you know, fact that in that direction for the thickness 2h. Now you come up with the final body. So the information of the geometry is completely described by the cross-section and the thickness. Yeah, is that clear? Because there is no variation of the geometry in the direction of the axis of the body. Okay. Now I will choose the reference coordinate system to simplify the formulation and also the solution procedure that I discuss later. Okay. So now I will choose X3 to direct along the axis of cylinder. Okay, X3 point along the axis of the cylinder. And X1 and X2 are contained in the cross section at the mid height. Okay, I look at the cross section, okay, located at the mid height of the body. And X1 and X2 are 2 coordinates, okay, or are 2 axes contained in that cross section. I don't have any specific preference for the direction of X1 and X2, but they have to be perpendicular to each other. But the direction can be arbitrary. Okay. So I don't have any requirement on the direction. Similar to the, you know, not similar, different from the previous case, because in Saint Vernon problems, I choose X1 and X2 to lie along the principal direction of the cross section, right? Okay, so but in this case, X1 and X2 can be in any direction, okay, except that, okay, it have to be contained in the cross section at the mid height, okay, and it have to be perpendicular to each other as well. There is no restriction on the choice of the origin O. Before I say that, okay, in Saint Vernon case, I pick the point O at the centroid of the cross section, but here it's not necessary. Okay, the problem that we look at here, so the origin O can be located at any point, you know, in the cross section at the mid height. Okay, is that clear to you? So now I will call X1 and X2 in plane coordinate. Okay, x1, x2 are termed the in-plane coordinates, okay? And x3 here is termed the out of plane coordinate, right? Out of plane in the sense that it's normal to the cross section of the body, okay? So x1 and x2 are termed the in-plane coordinates because they are contained in the cross section at the mid height, okay? If we define the coordinate system in this way, now I can say that the geometry of the body that we have here, or the geometry of the cylinder that we consider here, is independent of x3, right? So if you look at the cross section, okay, it's independent of x3, or the geometry of the whole body here is independent of x3. You don't need the variation you don't need the variation of x3 to describe the geometry of the body completely, okay? So now let's look at the material properties. The problem that we will focus on here, we look at the special class of material. So we say that, okay, the body is made of isotropic linear elastic material, but it can be non-homogeneous. Okay, so the material property can be a function of x. Okay. The next requirement. Okay, we look at only for the case that the material constant, because it's isotropic, right? You need to specify two material constants out of this set. We have five typical material parameters that people use in the literature. We have to specify two of them from this set, okay? Two from this set have to be prescribed. And also I have one more assumption or one more restriction on the material properties. They can be a function of position, but it cannot be a function of x3. Or I can say that the material property have to be independent of x3. So if you move along the x3 direction, you see exactly the same material properties. But if you move in the in-plane direction, you move to, you move arbitrarily in the cross section, you may see different value of the material properties. That's what I try to say, okay? So the material can be non-homogeneous, but it cannot, depends on x3. Okay, that is the restriction of the material property that we will focus on for this class of problem. Okay. How about the loading conditions? Okay, so we can have body force field. Compare with the previous class of problem, Saint-Bernard problems. In that case, we just simply say that, okay, the body force is 0. But in this case, the body force can be non-zero, but it cannot be a function of x3, okay? Or I can say that the body force field is independent of x3, okay? And also, the body force field cannot have the out of plane components, okay? So B3 have to be 0. So we look only at the case that the applied body force is non-zero only for the in-plane direction, and that non-zero body force are independent of x3. Or if you want to see it mathematically, so B1 can be non-zero. B1 simply the body force in x1 direction. So B1 can be non-zero, but it's simply a function of x1 and x2, not x3. Okay, and B2 can be non-zero as well, but it cannot be a function of x3. Okay, and B3 is identically 0. Okay, so this is the body force field that we will consider for this case. Is that clear to you? So this kind of body force field is somehow special, right? Compared with the general case. For the general case, B1, B2, B3 can be any value, and it can be a function of x1, x2, and x3. But in this case, we look at the loading condition that contained in the plane or contained in the cross section, because the outer plane distribution, outer plane contribution disappear. B3 disappear. So we don't have the body force normal to the cross section. You can say in that way. Okay, the body force is applied in the in plane direction, and also when you move from cross section to cross section, you move in X3 direction. You didn't see the difference of the body force field because they are independent of X3. Is that clear? Is that clear to you? Okay. So this kind of body force field, we can say that this is the 2D body force field. Okay, it's 2D in the sense that the vector that we use to describe the body force completely simply require only two components, B1 and B2, right? Because B3 disappear. Okay, so some people just say that, okay, this is the 2D body force field. Okay. How about the boundary conditions? Okay, if we look at the boundary condition, we know that, okay, the boundary of the body consists of 3 parts, right? Look at the side face first. Okay, the side face S pi. We look at the spatial case here. Okay, we say that, okay, the condition that we will focus on, we say that, okay, on the surface S pi, the outer plane traction have to be 0 everywhere. Okay, at any point on the side face, we cannot have loading applied in the third direction, in X3 direction, or I can say that the outer plane traction have to be 0. Okay, at every point on the side face. And how about the in-plane quantities? The in-plane quantity, I talk about the quantity in X1 and X2 direction. So we can prescribe the condition in the in-plane directions in 2 ways, similar to the 3D case. We can specify displacement, or we can specify traction in X1 and X2 direction. And those kind of traction or displacement have to be independent of X3. Okay, so this is the loading condition that we look at, or the boundary condition that we look at every point on the surface S pi. Okay, so we can think about that this is 2D boundary condition, right? 2D boundary conditions, because the outer plane traction is identically 0. Okay, so the in-plane, we can specify displacement, or we can specify traction as a function of X1 and X2. Okay, in X2 direction, we can do exactly the same way. We can specify displacement, or we can specify traction. Okay, so that's what we call the in-plane boundary conditions, or the boundary condition for the 2D case. Okay, because it's required to specify only 2 components of the displacement or the traction at any point along the boundary S pi. The outer plane boundary condition, we expect that, okay, that one is satisfied automatically. Okay, so we can say that we don't apply anything in the third direction. Okay, how about the top and bottom surfaces on the surface S1 and S2? So we have this kind of assumption. So the in-plane traction vanish at the top and at the bottom surface. Okay, what does it mean? So if you look at the top and bottom surfaces, you can apply the traction, right? The shear traction. The in-plane traction that I talk about at the top and bottom surfaces are simply shear traction, right? Okay, so we assume that, okay, the shear traction that apply at the top and bottom surfaces vanish. Okay, no shear traction apply at both ends. of the body. Okay. How about the out of plane quantity? We have two conditions that we have two conditions that we are interested in. The first condition, the traction in the normal direction is 0 too. Okay, so the out of plane traction is 0. Or the second case, we look at the out of plane displacement equal to 0. Okay, so there are two cases that we look at here. The first case, we look at the traction-free condition at both ends. So this condition combined with that one, that is the first case. We look at the body that's subjected to 0 traction in all directions at both ends. Okay, that is the first case we look at. The second case, we have the combination between this one and that one. Okay, the second case, we say that, okay, we don't have shear traction applied at the top and bottom surfaces. And we constrain the body to move in X3 direction at the top and bottom surfaces. You can think about the rigid block located at the top and at the bottom to prevent the movement in the normal direction. But it can slide freely in tangential direction. In that case, shear traction are 0. Okay, is that clear to you? So two types of the boundary condition at the top and bottom surfaces are considered here. The first type, we say that, okay, the traction are 0 in all directions at both ends. And the second type, we constrain the movement in the out plane direction, but we apply 0 shear traction. Okay, is that clear? So this is the problem that we are interested in. Okay, I talk about the geometry, I talk about the material property, talk about loading condition, talk about the boundary condition. All this information assumed in the way that I just mentioned. So this is the class of problem that we are interested in. Okay, so if you take a look at all the information that I introduced here, you can see that most of the information are in plane, right? The out plane simply 0, right? So we look at only the problem that involve the in-plane information, including the geometry, material property, loading conditions, boundary condition. All of them are in plane. Okay, and also they are independent of X3. So this is somehow spatial. Okay, and we look only at the spatial class of problem here, because several practical cases can also involve this kind of simple information. If that is the case, you can use this kind of setting to formulate the problem, because it will be simpler. You will see in a moment. Okay, a lot of things can be simplified. Instead of using the general setting, the general equation, general quantities, the general function of of the coordinates x1, x2, and x3, we can simplify those kind of things to make the problem simpler in the sense of if you want to determine the solution. If it's simpler, so you can have a simple way to get the solution as well. Okay. I have a remarks here. Okay, I hope that this will be useful to you. So if you look at the prescribed data that I mentioned before, so the geometry, the material properties, the loading condition, and the boundary condition, all those kind of data is independent of X3. And also, if you deal with the vector, the component of the vector in the normal direction to the cross section disappear as well. Okay. So what will we expect based on the problem that we have that kind of simple information? So if you deal with a simple body, simple geometry, simple material property, loading condition and boundary condition, because all of that information is simply the in-plane, right? Simply in-plane quantities and independent of X3. So based on that kind of data, I expect that, okay, the displacement, strain, and stress that induce inside the problem, induce inside the body should be independent of X3 as well, right? So that's what we expect, because the information that we prescribe there is independent of X3. So how the solution that we got is dependent of X3, it seems impossible, right? So this is the thing that should be clear to you, that, okay, the solution of the problem should be independent of X3 as well. Okay, or I can say that the displacement, strain, and stress shouldn't be a function of X3. So now you reduce the coordinates from X1, X2, and X3 to only X1 and X2. Okay, you don't need to worry about X3 variation anymore, because it should be independent of that coordinate, right? Because the data, the information is independent of X3. So the solution should behave in the same way. Okay. Also, like I told you, that the outer plane component of the field quantity should vanish too, right? Because we don't have the outer plane contribution. The data in the outer plane direction, a constant or even disappear. For example, the body force field that you apply, we don't have B3. We don't apply any loading condition in the X3 direction. Okay, and also the Barry condition on the side phase, you will not apply any traction in the X3 direction, right? So if that is the case, so the displacement, stress or strain, okay, in the components that involve X3 should disappear too, right? So that's what we expect. So if we can reduce some of the quantities, okay, or some of the quantity should disappear automatically due to the simplified information of the problem. So we expect that the number of field unknowns, if you remember, for the general three-dimensional problem, we have 15 unknowns, right? We have 3 displacement, we have 6 independent stress components, we have 6 independent strain components. Totally, we have 15, right? We expect that, okay, for the problem with this kind of spatial information, the number of field unknowns should be reduced. Okay, and also at the same time, the number of governing equations that we have to deal with have to be reduced too, right? So we expect that, okay, we should come up with something that's simpler than the general case. Okay. Also, because the field quantities are expected to be independent of X3. So the derivative with respect to X3 should disappear in the governing equation, right? So now we expect that the form of the governing equation, or the number of terms that appear in the form, appear in the governing equation, should be reduced. Okay, the form should be less complex, and also involve less terms, okay, in the equation, right? So we hope that will make things simpler. Okay. You may have very important question here. So the simplified setting that I mentioned here, is that practical? Is that possible for the practical problems? If you go back and think about this, I think there are several cases that you have to deal with in reality. Okay, have the problem setting similar to what I just mentioned. Okay, for example, if you look at very thin bodies, okay, for example, you look at the plate, the very thin plate, or the body that's very long. Okay, the length may be very large compared with the cross-sectional dimensions. So that if you look at those cases, you will see that, okay, some of the assumptions that I made here are valid. Okay, so that's why I try to think about this is the important class of problems, and try to talk about this as part of material in this class, because I hope that, okay, the thing that I show you here will be useful to you in the future, because solving a simplified problem is better than solving the complex problem. Okay, if you know that, okay, the problem you have to deal with, okay, involve the simplified set of data, there is no need to solve the problem in the general context, because it's complicated. So if we know that some of the information is simplified, so we can set up the problem in a simpler, in a simpler setting, dealing with less unknowns, dealing with less complicated equations. Okay, so now we can come up with some technique that can be used to solve that kind of simplify problem. Okay, do you have any question about anything here? I may not be able to go in detail for today, so I will stop here, and next time I will come back and discuss about two common types of conditions that you will face with in the future. If you have to deal with the the mechanics problem, you have to deal with the plane strain condition and plane stress condition. So these two conditions are very well known in 2D linear elasticity. Okay, so next time I will talk about this. Okay, if you have time, please go back and read the note that I gave you here. So prepare yourself to be ready before you come to the class, so I can discuss about this two concepts faster. Okay.